Hello everyone. It's a pleasure to be delivering this short session on hydrogen as part of the Youth Climate Summit. My name's Josh Bailey and I'm a director at the sustainability collective known as People Power. So, what exactly are we going to be talking about today? Of course, we'll be focusing on hydrogen, but I also want to explore fuel cells and how combined with hydrogen and used in the appropriate application, they can help tackle the problem of climate change and help us with decarbonisation. And this is particularly important because the UK has signed up to be net zero by 2050. So time is really of the essence. I also want to explain why I think engineering is an exciting pursuit and why you could all be green energy advocates of the future. So please, grab a piece of paper, a pencil, and be prepared for a few short exercises as we explore the green fuel of the future. So, what better place to start than hydrogen? I'm sure all of you have come across hydrogen, but here's just a quick reminder. It's the first and lightest element in the periodic table, and it appears over on the top left-hand side and has some rather interesting properties. But before we talk about those, I'd like you to draw up a table for me, like this. So I'd like you to draw up 5 columns and 4 rows. And what we're going to do is fill this in based on your knowledge of the charge and mass, and also thinking about how many of each of these subatomic particles are found in a hydrogen atom, and then how many are found in a hydrogen molecule. So from now, you have 1 minute to complete. And while you do that, I'll just remind you a bit about hydrogen. Remember, it's the simplest atom. It does actually come in 3 different isotopes. Remember, that's different numbers of neutrons. But we are only concerned with the most abundant one, technically known as protium, but also normally referred to as hydrogen. And it's actually the lightest element. It actually has hardly anything in the nucleus. And also, it's worth remembering when you consider an atom versus the molecule, we think about the atom, it's just this tiny little atom on its own. It can only bond to one other thing. And actually, normally when we have a molecule of hydrogen, which is how we would find it, it's bonded together as H2. Okay, so 2 hydrogen atoms make up the molecule. Hopefully that will help you with the last column. Okay, so you've had about a minute. So this is what you should have got. So in the first column, a neutron has no charge, an electron is negatively charged. The masses of the proton and the neutron are approximately the same, although the electron weighs much, much less. And of course, there are no neutrons in protium, in that lightest of isotopes of hydrogen. In a hydrogen atom, there's just 1 proton and 1 electron. And as we've just discussed, in the diatomic molecule, 2 atoms, it doubles up. There's 2 protons and 2 electrons. So we have this diatomic molecule, a molecule containing 2 atoms. And it's held together by a single, what's known as covalent bond, which is a shared pair of electrons. So that's 1 electron from each atom of hydrogen. But why is all of this important? Well, it's because this bond represents the chemical energy stored in the molecule. It's this strong covalent bond that glues those 2 protons together that gives hydrogen this great potential to be a fuel. In fact, it has a really high energy density per mass. So its energy density is between 120 and 142 megajoules per kilogram. And that compares to only about 50 megajoules per kilogram for petrol. So it's a seriously good contender as a fuel. It's also a colorless, odorless gas at room temperature. And it's actually by far the most abundant atom in the known universe, as you'd be able to see from the right-hand side. However, it easily bonds with other elements, so it's rarely found as this diatomic molecule. And actually, it's more commonly found bonded to oxygen, for example, in water, or nitrogen in ammonia, or carbon in methane or other hydrocarbons. So then the question becomes, how can we harness this wonderful power of this molecule if we don't just find it in nature as this H2 diatomic? Well, the answer to that question is that we don't consider hydrogen as an energy source, but instead as an energy carrier, or an energy vector, if you will. So if we can access hydrogen, and we need to do that in a clean way, let's say we get it from water, then later when we need that energy, we can combine that hydrogen back with oxygen to make water and give you back at least some of that energy. And to do that, we need engineering devices. Engineering devices to break the water called electrolyzers, and fuel cells as devices to put those hydrogen and oxygen molecules back together to make water and get the electricity back. So you've likely heard of electrolyzers, or at least electrolysis from GCSE chemistry, where you very safely put electricity through water and it splits into individual components, hydrogen gas and oxygen gas. And I'm sure a lot of you are also familiar with this opposite concept. A fuel cell is the opposite of an electrolyzer. It combines hydrogen and oxygen to give you the electricity, heat, and water. But perhaps few of you have actually seen a fuel cell. So I'd just like to take a moment to sort of show you a little bit about what a fuel cell looks like. So here's an example of a real fuel cell. And what you have is one side, which is where you put the oxygen, and another side where you put the hydrogen. And you have two electrical points. And so you can connect up a circuit. And if you put hydrogen on this side and oxygen on this side, you can get electrical power and make a bulb light up or turn a motor. But maybe we should go into a bit more detail. Let's take one of these apart. So what I've done is I've broken it down to sort of three main components. You have your current collectors. So these are on the outside. These are just bits of metal. They're electronic conductors. And those help us to take the electrons in and out of the cell where needed. And then in from that is you have these electrodes. So these are made from carbon with platinum. So a platinum electrocatalyst is used to catalyze the reactions that happen on the two electrodes. So on the anode, the oxidation of hydrogen, and on the cathode, the reduction of oxygen. And then finally, maybe the most important component, is a complex plastic material, which is essentially made to be a proton conductor and an electronic insulator. So it allows protons to flow, but doesn't allow electrons to flow. I want you to just draw up a schematic of a fuel cell. So you could just use simple lines and rectangles just to show the components that we've talked about. And remember, we had current collectors, and then we had electrodes, and then in the middle, we had a membrane. So okay, you have 1 minute to do this, and I'm going to just explain a little bit about what those components do, and then we'll revisit that schematic to really understand the functions of a fuel cell. So the electrodes that you draw, one of them is an anode and one of them is a cathode. And that means at the anode, there is oxidation. So oxidation of hydrogen in this case. So hydrogen comes apart, gives you protons and electrons. At the cathode, we have reduction. So oxygen is reduced. So oxygen diatomic molecule is also broken up and it's reduced to give you oxide. And so together these redox processes give rise to electrons that can travel around an external circuit. But remember, the electrons can't travel through the electrolyte. Only protons can. So the protons can travel through from the anode to the cathode, meet with your oxide to give you water. And the great thing is, if hydrogen is produced in a renewable way, this whole system of electrolyzing water and putting it back together, it doesn't create CO2. And it gives you back a significant amount of the energy that you put in without any particulate matter, without any NOx gases or SOx gases or unburnt hydrocarbons. So similar to a battery, this is a zero emissions way of creating electricity. Here, instead of charging up the battery and storing charge, we're using hydrogen as the energy carrier. And here's an example of such a schematic. Hopefully it looks a bit like yours, but you can always add more annotations to it as we're talking about it. So just to recap, how does a fuel cell work? The hydrogen comes in at the anode and it's oxidized, which means it loses electrons. So it splits apart into protons and electrons. And those protons, they can travel through the membrane, which is actually called a polymer electrolyte membrane in this type of fuel cell. Whereas electrons cannot, it's an electronic insulator. So the electrons have to go around the external circuit, which is where we get our usable electricity. And then the electrons combine with the oxygen at the cathode, reducing oxygen to oxide, or O2 minus. And because the protons have come through the membrane, they can combine with O2 minus to give us this water, H2O, as a byproduct. So hopefully now you've got a greater sense of exactly how a fuel cell works, or at least in this case, a polymer electrolyte membrane fuel cell, or PEM fuel cell. But often the next question is, Well, if it works so well as an energy carrier, why are we not using it more? Is it about safety? And the truth is, although hydrogen can be dangerous, so can all fuels. By their very nature, fuels are energy dense and therefore potentially dangerous. And this is true for petrol, diesel, LPG. But the truth is, if you're careful with fuels, if you put in the right engineering controls and safety practices, you can make them suitably safe and make them incredibly useful. So actually, in terms of hydrogen, it's not so much that it's an energy dense fuel, I mean, that's a part of it, but it's also, there's a worry because it has a wide flammability limit. So its lower flammability limit is 4% in air, and its upper flammability limit is 75% in air. And this flammability range is wider than other fuels. And this means there's a wider range of concentrations of the fuel in the air that give rise to a flammable mix. However, there are some very helpful properties of hydrogen that allow us to sort of mitigate that problem. So because hydrogen is lighter than air, remember we said it's the first and lightest element of the periodic table, it goes straight up. So if you have an ignition, you would get a flare that goes straight up into the air. Let's compare that with, for example, burning petrol or burning liquid fuels that would sort of pool around your vehicle and potentially cause more catastrophic damage. And because, again, it's the smallest molecule, it also has a very high diffusivity. That means it diffuses in the air and disperses extremely quickly. And combining these two main safety elements, lots of protocols can be put in place to ensure that actually you never reach those worrying concentrations and you ensure there's no ignition and therefore no fire or explosion from hydrogen. So I guess the message is that it's very important to have protocols in place to use hydrogen safely, as it is for other fuels. And there are various protocols in place, for example, in the first fuel cell electric vehicles which are out there, which I'll talk about in a moment. And it's very important also to note that the hydrogen industry is already vast. We use hydrogen on an industrial scale, not to the scale that we'd like to in a future hydrogen economy where we use it for many different applications. But at the moment, we still have a lot of safety protocols from existing infrastructure which allow us to move towards the hydrogen economy. So I mentioned that we already have safety protocols. So here is an example of a fuel cell electric vehicle. And after 20 years of research, this car, the Mirai, the Toyota Mirai, is an example of including many of these different engineering controls to minimize, for example, the risk of leaks, or to detect leaks if they do happen, to shut down tanks in that event, or to even prevent impact to the tank, or even if there is impact, to make sure that they can withstand high impact events. And if you want to find out more information about the Toyota Mirai, there's some URLs below. So we know what hydrogen is, and how useful it can be, and how it can be made safe. So how does it help us in the fight against climate change? Well, we know that we want to move away from burning fossil fuels, so we need to reduce our greenhouse gas emissions. So what we need to concentrate on is therefore creating green hydrogen. And if you hear these different terms like grey or blue or green hydrogen, they're about how the hydrogen is produced. And green hydrogen is produced by using renewable energy sources, so that you're not creating a lot of greenhouse gas emissions in transferring energy to this energy carrier. So once we scale up our ability to make green hydrogen, the idea is then to use that green hydrogen in various different decarbonisation efforts. And that means working out which industries can benefit most from green hydrogen. So as activity 3, I'd like you to write just a short list, maybe 3 different areas that you think could be decarbonised potentially by using hydrogen. So whilst you're doing that, I just want to highlight it'd be really useful to think about which sectors of society are currently burning a lot of fossil fuels. We've already talked a bit about passenger vehicles, but there's many other areas in which we use these fossil fuels. Where might we be able to switch away from them and use hydrogen instead? Okay, we might be able to reduce emissions by electrification in some areas, but other sectors, it's a bit more difficult. Which sectors could we struggle with? Where could hydrogen be useful? Okay, so you've had about a minute now. So I should take a look at your list and see if any of them overlap with some of the areas highlighted here that the hydrogen industry is looking at. So, First application to talk about is transportation, and this is bigger than passenger vehicles. In fact, there's a lot of talk that passenger vehicles, it might make more sense generally to use a pure battery electric vehicle. But actually, hydrogen fuel cell electric vehicles and pure battery electric vehicles don't necessarily have to compete. They're just looking at different applications. They complement each other. In fact, there's a lot of talk about using hydrogen in heavier or larger vehicles, such as trucks and trains and ferries. And the idea being that as you make the vehicle larger and you require a bigger powertrain, batteries maybe just get a little too heavy. And actually, hydrogen can provide you the short fill-up times and the long distances that maybe battery electric vehicles can't deliver. But equally, battery electric vehicles are great for shorter length journeys and for city driving. A good example of this is the Nikola One from a company called Nikola, off of Nikola Tesla. And so fuel cell electric vehicles are starting to come out, which can be longer distance, heavier transportation compared to your normal passenger vehicle. And if you want to find out more about Nikola, you can take a look at the link below. But we also have another type of application of hydrogen. So beyond transportation, hydrogen is also seen as a viable option for grid scale storage, so storing energy at the sort of national scale. And this is increasingly important with renewable electricity, right? Because renewable electricity is intermittent. Sometimes it's on, sometimes it's off. So hydrogen is seen as particularly attractive as it could allow seasonal storage. So you could be storing energy from summer when the sun is shining and use some of that energy when it's no longer sunny, when you move to the darker months. So it's sort of seen as a great way of bridging the gap, the intermittency gap, and it can kind of complement the shorter term storage offered by traditional batteries. A further application is looking at some of those really hard to decarbonize areas. So there's some areas such as industrial heating or heating even of our homes, but I just want to focus here actually more on the industrial chemical making side of things. So there are companies that are looking at using green hydrogen to significantly limit the greenhouse gas emissions associated with ammonia production, which we make a lot of for fertilizers, but also potentially for steel making. So here we've got just a depiction of how it could be used as a different route, rather than the traditional blast furnace route, how we could use hydrogen to decarbonize steel making. So I've given some examples of applications. So these are things that governments and companies get involved in. But how can you get involved? How can you be involved in this energy transition? Well, for a start, the UK is crying out for engineers. We've had a shortage of skilled engineers for some time, but as recently as 2019, as I show here, there were worries about shortages in over 50% of engineering and technology firms. So if you train to be an engineer, there are plenty of jobs out there. In fact, I started out as a chemist and have ended up as a chemical engineer working in an amazing research group at UCL called the Electrochemical Innovation Lab. And although chemical engineering is wider still, even in the EIL, we have been focusing on a whole host of areas, including batteries, fuel cells, electrolyzers, supercapacitors, CO2 conversion, and much, much more. It's a really exciting research area to be involved in. And there's a real need to attract more students to chemical engineering and other disciplines that are associated with these electrochemical devices. It really is an exciting area where you're challenged every day to think of solutions to complex problems. But you have the sense that your work has a direct and positive impact on society. It also happens to be a sector of growth and one which is well paid, so do consider it before making your next study decision. And to conclude, I'd like to leave you with a vision, an action, and a call to those at COP this time around. We envision a world in which the hydrogen economy supports a net zero future. We really hope that hydrogen plays a bigger part in our fight against climate change, and its role only grows in the 2020s. A simple action that you can take is to ask your teachers more about hydrogen, and particularly about the ways in which it can help decarbonize and reduce greenhouse gas emissions. Maybe ask them about what is grey hydrogen or blue hydrogen or green hydrogen, about how hydrogen can be used to decarbonize steel making, or about those other transportation types that seem to be coming online across the world. How can hydrogen technology be used to fight climate change? And finally, To the leaders of COP, please invest more in green hydrogen and support the rollout of more subsidies to support its use in heavy-duty vehicles. Please back hydrogen as a key part of industry decarbonisation. Thank you all for listening. I hope you enjoyed it.